Hey, it's Mr. Dean. This looks like part two of what's growing to be a three-part series of graphing rational functions. And now in this video, we're going to use or look at a couple of examples where the numerator is less than the denominator in terms of the degree. So if you have to go back to the first video, make sure you do. Otherwise, you don't know what we're talking about when we talk n and m and whatnot. So here is an example of numerator degree is 1, and the denominator degree is 2. So they're not equivalent. And what that means, what it does to a graph, has mostly to do with the horizontal asymptote. So let's get to that in a moment. But first, let's try to factor the numerator and denominator. And you're not, in this case, going to have any success, not over the real numbers. So there's no factoring to be done. But you really want to make sure that every time you see a new example that you do try to factor first. So I want to emphasize that we always try to factor. If you skip factoring, it is going to make it a much harder problem. You're probably going to get it wrong. So make sure you factor first. But in this case, neither of these are factorable, so we're stepping on to number 2. Horizontal asymptotes. Horizontal asymptotes are what happens when the x gets really large. And as x gets really large, that's where they say it in calculus, plus or minus infinity, as x goes there, the value of the function goes to what? Does it go to a certain number, or does it wave back and forth like a sine wave? Well, let's just kind of think about this. If I plug in x equals 1, it's not very large, I will have 5 over 3. Not very big. If I plug in x equals 100, I will get 401 over, let's see, 20,001. All right, 5/3 is way bigger. If I plug in, let's move on over here, x is like 1,000, then the value of y will be 4,001 over 2,000,001. That is way less than the 401 number. In other words, we are getting smaller and smaller, and as x gets even larger, so we're eventually going to approach a number pretty close to 0. Every time the numerator is less than the denominator, every time we have a horizontal asymptote that reflects that. Y is going to be equal to 0. So this graph is basically, from a distance, a flat line at 0. It's pretty boring for large values of x. Now it gets interesting for small values of x, and that's what we're going to focus on. Number 3, the vertical asymptotes are the zeros of the denominator. Same idea with polynomials, right? So we have zeros just the same. So we look here, is there any zeros there? We didn't factor it. Not factorable. There are none. All right? So a horizontal asymptote is at y equals 0. A vertical asymptote, we don't have any. It's going to be a continuous graph from left to right. There's no stoppages. So we're kind of stuck with just, if you look at the graph now, we haven't really done a whole lot. So now is the time we plug in a few smart x's, a few smart inputs, and try to figure out what's going on in the table here. So sometimes a really easy one, oftentimes, is just find the y-intercept, plug in 0 into your equation, and when we do that, we get out 1. Got ahead of myself there. When we plug in -1 into our equation, we get out -1. Our x-intercepts is a little harder, but not that bad. Our x-intercepts are, in the world of polynomials, just think of the numerator as its own polynomial. What is the 0 of 4x plus 1? Right, that 0 is -1/4. So you kind of get a free one there as well. If it's not easy to find the x-intercepts, you don't really always need them, because we're just doing kind of a qualitative graph. We don't have to graph every single point. So some other smart numbers that are small, easy to plug in, are 1, and you get 5/3, and I chose to plug in a 2, because that was pretty small and easy. All right? I don't really want to plug in too many more numbers than about 5 or 6, because once you start plugging in 8 numbers, 10 numbers, you're starting to plug in everything, and it's just going to take you all day, and you're not taking advantage of some of the shortcuts. So let me get my scale on here, and you can get your scale going in your notes I'm not going to get much further than 3 in any direction. And I'm going to very simply just plot the points. So we got 0, 1. I've got 1 and 5/3. I've got 2 is 1. I've got negative 1/4, 0. All right, now finding that number right there, the x-intercept, was kind of big. Here's why. Because I know as these two go across, those 2 points connect, that as I get larger and larger x's, I must approach 0. I must approach that red asymptote. As it gets closer here, I must connect these. But watch, it goes right through, yes, right through the horizontal asymptote. Talk about that more in a moment. But as I get further and further away, relatively large values of x, I get sucked back in to the asymptote. It's like a magnet that brings it closer. All right. For small values of x, negative 2, negative 1, 0, 1, and 2, for small values, I don't have to be near the asymptote. I can get kind of far away from the horizontal asymptote. But relatively large numbers, and you go back to the problem, by relatively large, in the problem there was a 4, a 2, a 1. The numbers aren't very large. So numbers like 3, 4, 5, 6, those are relatively large. And as you get out to those spots on the graph, you're going to be sucked into the horizontal asymptote. But we cross the horizontal asymptote at a really small number, negative 1/4. All right, it is possible to cross the horizontal asymptote. So that's your graph. Let's take a look at what it looks like from a more official smartboard kind of way. The scale is a little bit different here. This is 2 way up here, so that's why it looks a little vertically stretched comparatively. But it looks pretty neat. Neat graph going through the x-axis. Let's do one more example here. So once again, kind of a larger denominator here, a little bit more complicated. Number 1, try to factor. All right, top is just x minus 2. Got that. Denominator, let's see if we can factor this. Let's see. Probably a minus 3 to plus 1. Does that work out? So with the middle, we got 2x squared. We have 2x. We have minus 3x. So that 2x and the minus 3x will make the minus x in the middle. And our last term, negative 3 times 1. Yep, it works out. So we factored it. Check. Number 2, remember, same thing. Horizontal asymptotes are always the end behavior. Compare the degrees. Well, once again, when the numerator is less than the denominator, we have a horizontal asymptote at y equals 0. As x gets larger and larger, this graph is just going to flatten out. Great. Number 3, the vertical asymptotes are the zeros of the denominator. Unlike this last example that we did in the other page, this does have zeros. They are at negative 1 for that one, right? And for here, I'm going to have 3 halves, or 1 1/2. Great, 2 zeros. There they are. Let's graph them while we remember it. Negative 1 is a 0, and 1 1/2 is a 0. All right, notice both of them are right along the horizontal asymptote. That is okay. That's it for asymptotes. Number 4, plug in a few smart x's in a table. Now I had a 4-function calculator. All right. Let me put, sorry. These were vertical asymptotes at those spots. They're not going to be crossing at the horizontal asymptote. My bad. I misspoke. But now, so we have these. I'll make this kind of the same color. So we have these 3 asymptotes. We've got 2 vertical and 1 horizontal. We're kind of done. Time to plug in some numbers. And I had a 4-function calculator. So when I talk about plugging in smart x's, I'm talking about plugging in x's to the left and to the right of each of those vertical asymptotes. So that vertical asymptote was at negative 1, so I plugged in negative 1.1. All right, I just put it into a little 4-function calculator. I got negative 5.96. I did it for all these other numbers. It was easy to plug in 0. I got 2/3. And I found the x-intercept already. That was 2, 0. All right, so the x-intercept is the 0. Well, let me make it a different color. Let's go with black. So I do cross the horizontal asymptote. It was just over there. All right, now, graph all these numbers. So I don't have to be super accurate, but negative 1.1 is a little bit to the left of my vertical asymptote, and we're going to be down there. My next number, negative 0.9. So that's just to the right of this asymptote, and we're way up here. All All right. And then 1.4 is to the left of this rightmost vertical asymptote. 1.4, and I've got a positive number right in there somewhere. Took care of it. But I go on the other side of the asymptote, and now I'm down at 0.77, somewhere-ish in there. The 0 is about 2/3, so we'll call it right about there. And we already took care of the 2, 0. All right. You got these kind of almost like a scatter plot here, but believe it or not, you have all the information needed to finish your graph. Let's work on the left side first. All you have is this one dot. That one dot by itself there, but you actually can figure out what it does. It has to be trapped in this little quadrant of asymptotes. All right? It must go along and finish the left arrow over there, and it must go along this vertical asymptote downward there. So we took care of that dot. Once we know that, we know there's no graph above it because it wouldn't be a function. In the middle here, I kind of got a pattern. If you look at it, it must go along asymptotes. All right, now come down here. Now remember we said we could cross the horizontal asymptote, but I know we don't cross the horizontal asymptote here for 2 reasons. Number one, well, I didn't find any x-intercepts. There weren't any zeros of the numerator other than the 2. And that 2 is right there. So I'm going to come back, and I got to hit that point. That's the other reason. I got to hit that point coming up. So I have a U shape there. And I'm going to follow along the horizontal asymptote to touch that dot. But here I'm going to cross. And once I cross, I'm kind of up above that horizontal asymptote, and it must just follow along. All right. I know I'm not just all of a sudden going to cross through that through that horizontal asymptote, because remember, the only place we do cross is at 2. So it must kind of float along like that. Let's take a look at what the calculator says. Oh, it looks good. Yep, and there's where it crosses. The scale makes it look like it's maybe a little closer than it is, but you can see the asymptotes go right across. You can see that those invisible asymptotes are bending the line away. Awesome job. People, that is it. 2 examples. It just takes a whole lot of examples to get used to it, so we'll do more in class. And we will see you then. See ya.